analyzed associates of the obese case study, the researcher was interested in the effects of two variables possibly affecting ratings of a male job applicant who appeared in an interview with a companion. 1. Whether the companion was obese or of typical weight, and 2. Whether the companion was a girlfriend or just an acquaintance. One approach would have been to conduct two separate studies, one investigating the effect of the companion's weight and one investigating the effect of the relationship to the companion. However, it is more efficient to conduct one study that includes both independent variables. Moreover, there is a much bigger advantage than efficiency of including two variables in the same study. It allows a test of the interaction between the variables. There is an interaction when the effect of one variable differs depending on the level of a second variable. For example, it is possible that the effect of having an obese companion would differ depending on the relationship to the companion. Perhaps there is more prejudice against a person with an obese companion if the companion is a girlfriend than if she is just an acquaintance. If so, there would be an interaction between the obesity factor and the relationship factor. There are three effects of interest in this experiment. Weight. Are applicants judged differently depending on the weight of their companions? Relationship. Are applicants judged differently depending on their relationships with their companions? Weight times relationship interaction. Does the effect of weight differ depending on the relationship with the companion? The first two effects, weight and relationship, are both main effects. A main effect is the effect of a variable averaging over levels of all other variables. It is convenient to talk about main effects in terms of marginal means. The marginal mean for a level of a variable is the mean of the means across all levels of the other variable. For example, the marginal mean for the level obese is the average of girlfriend obese and acquaintance obese. This table shows that this marginal mean is equal to the average of 5.65 and 6.15, which is 5.90. Similarly, the marginal mean for typical is the average of 6.19 and 6.59, which is 6.39. The main effect of weight is based on a comparison of the marginal mean for obese with the marginal mean for typical. Similarly, the marginal means for girlfriend and acquaintance are 5.92 and 6.37. In contrast to a main effect, which is the effect of a variable averaged across levels of another variable, the simple effect of a variable is the effect of the variable at a single level of another variable. The simple effect of weight at the level of girlfriend is the difference between the girlfriend typical condition and the girlfriend obese condition. The difference is 6.19 minus 5.65, which equals 0.54. Similarly, the simple effect of weight at the level of acquaintance is the difference between the acquaintance typical condition and the acquaintance obese condition. The difference is 6.59 minus 6.15, which equals 0.44. Recall that there is an interaction when the effect of one variable differs depending on the level of another variable. This is equivalent to saying that there is an interaction when the simple effects differ. In this example, the simple effects are 0.54 and 0.44. As will be shown, these simple effects are not significantly different. The important questions are not whether there are main effects and interactions in the sample data. Instead, what is important is what the sample data allow you to conclude about the population. This is where analysis of variance comes in. Analysis of variance tests main effects and interactions for significance. An analysis of variance summary table for the data is shown here. Consider first the effect of weight. The degrees of freedom, df, for weight is 1. The degrees of freedom for a main effect is always equal to the number of levels of the variable minus 1. Since there are two levels of the weight variable, typical and obese, the df is 2 minus 1, which equals 1. We will skip the calculation of the sum of squares, SSQ, not because it is difficult, but because it is so much easier to rely on computer programs to compute it. The mean square, ms, is the sum of squares divided by the df. The f ratio is computed by dividing the mean square, ms, for the effect by the mean square for error. For the effect of weight, f equals 10.4673 divided by 1.6844, which equals 6.214. The last column, p, is the probability of getting an f of 6.214 or larger, given that there is no effective weight in the population. The f distribution depends on the degrees of freedom for the effect and the degrees of freedom error. The degrees of freedom for an effect is the number of levels of the effect minus 1. Here, weight has 2 levels, obese and typical, and therefore the degrees of freedom for weight is 2 minus 1, which equals 1. The degrees of freedom error is equal to the total number of observations, 176, minus the number of conditions, 4, since there are 4 possible combinations of weight and relation, which equals 172. The p-value for an f with 1 and 172 degrees of freedom is 0.0136, which is quite low, and therefore the null hypothesis of no main effect of weight is rejected. The conclusion is that the weight of the companion affects judgments of the candidate's qualifications. The effect of relation is interpreted the same way. The conclusion is that being accompanied by a girlfriend leads to lower ratings than being accompanied by an acquaintance. The degrees of freedom for an interaction is the product of the degrees of freedom of variables in the interaction. For the weight times relation interaction, W times R, the degrees of freedom equals 1, since both weight and relation have 1 degree of freedom. 1 times 1 equals 1. The error degrees of freedom are the same for all effects, 172. The p-value for the interactions f of 0.062 with 1 and 172 degrees of freedom is 0.8043. Therefore, these data provide no evidence for an interaction. Always keep in mind that the lack of evidence for an effect does not justify the conclusion that there is no effect. In other words, you do not accept the null hypothesis just because you do not reject it. When there are equal sample sizes, the sum of squares total will equal the sum of all other sums of squares. However, when there are unequal sample sizes, as there are here, this will not generally be true. The means as a function of weight and relation are shown in this plot. Although the plot illustrates the main effects as well as the interaction, or lack of interaction, it is called an interaction plot. It is important to carefully consider the components of this plot. First, the dependent variable is on the y-axis. Second, one of the independent variables is on the x-axis. In this case, the variable is weight. Finally, a separate line is drawn for each level of the other independent variable. This example uses data from a hypothetical experiment. 12 subjects were selected from a population of high self-esteem subjects, and an additional 12 subjects were selected from a population of low self-esteem subjects. Subjects then performed on a task, and independent of how well they really did, half were told they succeeded, and the other half were told they failed. Therefore, there were 6 subjects in each esteem success combination, and 24 subjects altogether. As you can see, the only significant effect is the outcome times esteem, O times E, interaction. Clearly, the effect of outcome is different for the 2 levels of esteem. For subjects high in self-esteem, failure led to less attribution to oneself than did success. By contrast, for subjects low in self-esteem, failure led to more attribution to oneself than did success. Notice that the 2 lines in the graph are not parallel. Non-parallel lines indicate interaction. The significance test for the interaction determines whether it is justified to conclude that the lines in the population are not parallel. Lines do not have to cross for there to be interaction.